Hello everyone. Welcome to the fourth session on the semiconductor fundamentals. In this session, I'm going to discuss the p-n junction. Having investigated the characteristics of extrinsic n-type and p-type materials in the prior session, we shall continue by examining what happens when these two materials are combined into a single device. It is critical to understand that when we combine p and n-type materials, we do not do so through simple mechanical means. Rather, we must maintain a single piece of monocrystalline silicon, not a polycrystalline amalgam of individual pieces. This can be achieved via a diffusion or ion implantation technique that is applied repeatedly to a single piece of silicon crystal. This will leave regions or zones in the crystal that are n-type or p-type. In fact, it is quite possible to have a region of one type completely embedded within a region of the opposite type, as we shall see in upcoming sessions. By creating a single zone of n material adjacent to a zone of p material, we wind up with the p-n junction. The p-n junction is arguably the fundamental building block of solid-state semiconductor devices. p-n junctions can be found in a variety of devices, including bipolar junction transistors and junction field effect transistors. However, the most basic device built from the p-n junction is the diode. Diodes are designed for a variety of uses, including rectifying, lighting, and photodetection. We shall begin by examining the basic structure and operation of the p-n junction. If we were to create a region of n material joining or neighboring a region of p material in a single crystal, an interesting situation occurs. Assuming the crystal is not at absolute zero, the thermal energy in the system will cause some of the free electrons in the n material to fall into excess holes of the adjoining p material. This will create a region that is devoid of charge carriers. In other words, the area where the n and p materials join is depleted of available electrons and holes, and thus we refer to it as a depletion region. This is depicted in figure 1 here. The excess electrons of the n material are denoted by minus signs, while the excess holes of the p material are denoted with plus signs. At the interface, the free electrons have recombined with holes. When an electron recombines, it leaves behind a positive ion in the n material and produces a negative ion in the p material. We now have a region depleted of charge carriers, and this will have an effect on the ability to establish a flow of current through the device. We have, in essence, created an energy hill that will need to be overcome. To understand the concept of energy hill, recall that in the previous session, it was discovered that doping an intrinsic crystal would shift the Fermi level. For n material, the Fermi level is shifted up toward the conduction band. In contrast, for p material, the Fermi level is shifted down nearer to the valence band. This is indicated in diagrams here. When two dissimilar regions adjoin, as in the case here, the energy bands will adjust so that the Fermi levels are consistent. Effectively, this causes the bands of the p material to rise relative to the bands of the n material. The interface between the two appears as a hill, and this is the aforementioned depletion region. This situation is depicted graphically in figure 2. This in fact is the energy band diagram of the p-n junction. When I compare this energy diagram to the energy diagrams of the n and p materials presented here, we understand there is a change in the energy level when we move from either n or p material towards the opposite material. By simply aligning the Fermi levels, it should be clear how we arrive at the new energy diagram that is indicated here. Now, let us consider what happens if we were to connect this device to an external voltage source as shown here. Obviously, there are two ways to orient the p-n junction with respect to the voltage source. This version is termed the forward bias, and the version is in fact the one I am showing in the diagram here. The dotted line in the figure here shows the direction of the electron flow. First, electrons flow from the negative terminal of the battery toward the N material. In N material, the majority charge carriers are electrons, and it is easy for these electrons to move through the N material. Upon entering the depletion region, if the supplied potential is high enough, the electrons can diffuse into the P material where there are a large number of lower energy holes. From here, the electrons can migrate through the positive terminal of the source, completing the circuit. Here, the resistor has been added to limit the maximum current flow. Now, the trick here is to assure that the supplied potential is large enough to overcome the effect of the depletion region. That is, a certain voltage will be dropped across the depletion region in order to achieve current flow. This required potential is called the barrier potential or the forward voltage drop, or as commonly known is the threshold voltage. The precise value of this depends upon the material that is used. For silicon devices, the barrier potential is usually estimated at around 0.7 volts. For germanium devices, it is closer to 0.3 volts, while LEDs may exhibit barrier potentials in the vicinity of 1.5 to 3 volts, partly depending upon the color. Another way of thinking about this is that the addition of the voltage source flattens the inherent energy L of the junction. Once the applied forward bias voltage is at least as big as the hill, current flow can easily start. If the voltage source polarity is reversed in the diagram shown here, the behavior of the PN junction is altered radically. In this case, the electrons in the N material will be drawn toward the positive terminal of the source, while the P material holes will be drawn toward the negative terminal, creating a small short-lived current. This has the effect of widening the depletion region, and once it reaches the supplied potential, the flow of current ceases. In essence, we have increased the size of the energy hill. Also, further increases in the source voltage only serve to make the situation worse. That is, the depletion region simply expands to fill the void. Ideally, the PN junction acts like an open circuit with an applied reverse bias voltage. This asymmetry in response to a supplied potential turns out to be extraordinarily useful. Perhaps the simplest of all semiconductor devices is the diode. In its basic form, a diode is just a PN junction. It is a device that will allow current to pass easily in one direction but prevent current flow in the opposite direction. We can quantify the behavior of the PN junction through the use of an equation derived by William Shockley, where we have equation given as I, which is the diode current, equal to Is, which is the reverse saturation current, multiplied by e to the power of Vd into Q divided by Kn capital T minus 1, where Vd is the voltage across the diode, Q is the charge of an electron, which is 1.6 into e to the power of minus 19 coulombs. N is the quality factor, typically between 1 and 2. K is the Boltzmann constant, given by 1.38 into e to the power of minus 23 joules per Kelvin. And lastly, capital T is the temperature in Kelvin. At 300 Kelvin, the quantity Q by K into T is approximately 38.6. Consequently, for even very small forward positive voltage, the minus 1 term can be ignored. Also, the reverse saturation current Is is not a constant. It increases with temperature, approximately doubling for each 10 degrees Celsius rise. If we plot the Shockley equation using typical values for a silicon device, we arrive at the curve shown here. This plots the junction current as a function of the forward positive device voltage. It is a representative curve only. While all silicon diodes will exhibit this same general shape, the precise value of current for a specific voltage will vary depending upon the device design. For potentials below 0.5 volts, the current is virtually non-existent. Above this, the current rises rapidly, becoming nearly vertical after approximately 0.7 volts. If the plot was recreated using a higher temperature, the effect would be to shift the curve towards the left, that is, a higher current for a given voltage. If we were to alter the graph to use a logarithmic current scale rather than a linear scale as we are looking at the graph here, we would come and end up with the graph as shown here. The resulting straight line plot shows clearly the logarithmic relationship between the diode's voltage and current. For negative voltages, that is under reverse bias, the Shockley equation predicts negligible diode current. This is true up to only a point. Also, the equation does not model the effects of breakdown. When the reverse voltage is large enough, the diode will start to conduct, and this is shown in figure here. In the first quadrant, we see the same general shape we found in the previous diagram shown here, where in the diagram shown here, Vf is the knee voltage or threshold voltage, which is roughly around 0.7 for silicon. IR is the reverse saturation current, which is ideally 0, but in reality, a very small current will flow through the device. Lastly, VR is the reverse breakdown voltage. Note that the current increases rapidly once this reverse voltage is reached. In general, diodes should not be operated in the breakdown region, except being the Zener diodes. There are two mechanisms behind this particular phenomena. First one is the Zener effect, named after Clarence Zener, which predominates when the doping levels are high and produces breakdown voltages below roughly 5 or 6 volts. It is due to the production of a very high electric field across the depletion region, which then results in the production of a very high current through electron tunneling. In devices using lower levels of doping, avalanche breakdown dominates. In this instance, a high electric field accelerates the free electrons to the point where they can impact surrounding atoms and create new electron-hole pairs, thus creating a new free electrons that can repeat the process, resulting in a rapid increase of current. The schematic shown in symbol 9 here is for a basic switching or rectifying diode. This in fact is the ANSI standard which predominates in North America. The P material is the anode while the N material is the cathode. As a general rule for semiconductor schematic symbols, arrows point toward the N material. In this case, the arrow also points in the direction of easy conventional current flow. Again, figure 10 here shows an alternate schematic symbol. This is the IEC International Standard. The difference being that it is in outline form without the body being filled in. So, to summarize, in this session, we have discussed about the creation of a PN junction, its working under forward and reverse biased conditions, its energy level diagram, and its VI curves. In my next session, I will discuss on different types of diodes available, such as Zener diode, light emitting diode, photodiode, etc. Well, with that, I end this session and I hope it was informative. Thank you.